right, so, nope, not complex 1, complex 2. So this is our second of 3 lessons on complex numbers. Today's Wednesday. I don't know if I'll have complex 2 do this Friday. I think I'm just going to have complex 2 and complex 3 do next week. Now, just a couple of reminders, administrative items. Next Friday is, some of y'all know, y'all are in Stuco. Field day, yeah, house party, half day, field day version. So we're not going to be meeting. None of our classes are going to be meeting. I think you will report here actually for third period attendance or whatever, just the beginning. But anyway, so that means our knowledge check. If you look there, our knowledge check is on Thursday, and we might have a couple of work days in between now and then. Just depends on if we can get through all this stuff. So. You just go on your table, that'll be fine. So here we go. Complex numbers in trig form. So yesterday we learned about complex numbers. They take the form a plus bi, where I is the square root of -1. And a lot of times in mathematics, we will assign a variable to represent a complex number, and we will use the variable z. I put a little line there, so it's a little bit too, I think. But we'll say z is equal to a plus bi. What's interesting, and this is kind of a thing that mathematicians do, is we want to graph this number. How do you graph a complex number? Okay, well, if you recall, this is the way that you're used to graphing things, okay? Where you have an ordered pair, like 2, 3, where this is a real number and this is a real number, and the first number you plot on the real x-axis, and the second number you plot on the real y-axis. In fact, we even dealt with those polar graphs for the last 2 weeks in situations where you had a different sort of graphing situation. But what we're going to do is, let's say I have the complex number 2 plus 3i, I can turn that into an ordered pair, 2, 3, but in this case, I realize, and you realize, since we're all math students and teachers here, that this number right here corresponds to the real part of that number, and this right here corresponds to the imaginary part. So this is one thing that mathematicians get in trouble on a lot. We have this parentheses, number, comma, number, close parentheses, but it means different things depending on the situation that you're in. All right? If I say this represents a complex number, then you realize that that is the real part and that's the imaginary part. But if I say this represents a real ordered pair, then I know and you know that that's a real number and that's a real number. So what we can actually do is we can plot this, and you can say, well, how can I plot things? I've got 2 real axes, and you say, well, who said that that axis has to be real? Why don't I just call that the imaginary axis? Where I'm going to plot the real part on the real axis and the imaginary part on the imaginary axis. And when you do that, you get 2 here, 1, 2, 3 there, and there's the point. This right here represents complex number z. It's kind of a weird way of thinking about it. That's a point which actually has 2 coordinates, whatever, but or that's a number. I guess you could say that's the number plot negative 4 plus 2i on, this is the real and this is the imaginary, and I want to call that one M. What would I do, class? How would I plot that point? Starting from the origin. Left, right, up, down. Good, Lonnie. Left 4. And then keep going. Up 2. There you go. That's the point M. That's the complex point M. Appreciate that. So it sounds kind of complicated, plotting a complex number, but is it really? No, it's not. It's literally just stuff you've been doing since, like, junior high or maybe upper elementary, plotting those 2 points. Now, this is something new, okay? What we can do, because this is a point, we can talk about the magnitude of a complex number. So we can put those magnitude bars around it, and we would say that equals the magnitude of complex number z. When we had real numbers and we do the absolute value bars on it, it's not too bad. Like, Trey, what's the absolute value of the real number 6? Yeah, 6. Grace, what's the absolute value of the real number negative 17? Yeah, those are, I should say absolute value, or what's the magnitude of negative 17? 17. All right, well, what's the magnitude, though, of 2 plus 3i? The magnitude is the distance from the origin to that point. Now, does anybody know a way that we could find the magnitude? Now, Ellie, I'm looking at you here on this one. Any idea how we could solve that? We could find the great. Any idea how we could find that magnitude? Magnitude is that distance right here. I'll give you. You would say it's the answer to every question in trig. Pythagorean theorem, that's right. You didn't think we would talk Pythagorean theorem this late in the year, did you? Probably not. Yeah, but that's it. So we can calculate the magnitude of a complex number by doing the square root, the sum of the squares of its real part and its imaginary part. So the magnitude there is going to equal the square root of 2 squared plus 3 squared. So that's 4, that's 9, so square root of 13. So we could say the magnitude of z, I might draw a little bit. 1, 2, 1, 2, 3. So there's the point z. It's not a vector, all right? It's a complex number, and this is the actual point. But when you talk about its magnitude, then we're talking about that length right there. But we can also talk about its angle. Now this gets really weird. The angle of a number. And we call that theta. So 3 there, and 2 there. Taking a request from anybody, or not requests, but suggestions from anyone. What do y'all think would be a way of finding theta in that situation? It's not too different from what we've done before. Go ahead, Robert, you got an idea for us? What's that? Arctangent, inverse tangent, yeah. we could say, I'll write it as tangent of theta would be 3 over 2, and so therefore arctangent or inverse tangent of 3 over 2 is going to give us theta. And we've done this so many times. We did this with polar coordinates, right? When we had the x component, the y component of a rectangular part, so we were going to try to convert it into arc theta. We did this with vectors when we had the x component, the y component of a vector, and we wanted to find the magnitude and direction of a vector. We did this just in regular time when I said, all right, here's a point, here's the terminal side of a ray. I want you to, find the angle of, that creates that. So this process, Pythagorean theorem and inverse tangent, and then the similar one, x sine theta, or x cosine theta, or x equals r cosine theta, y equals r sine theta. Those processes we just use all the time. So in general, so it's sort of like, here's the, so if you have z equals a plus bi, the magnitude of z would equal the square root of a squared plus b squared, and theta would equal inverse tangent b over a. That's just sort of generalizing what we saw here with the numbers 2 and 3. And like I mentioned a second ago, remember how we saw this many times, this formula. I know you've written it down. X equals r cosine theta and y equals r sine theta. You don't need to write it down necessarily. I'm just going to write y'all have seen this? Give me a head bob here. Let's rewrite this using complex number notation here. So what we have been calling the x and y correspond to the a and b, right? Where a has been sort of our horizontal and b has been our vertical. So instead of saying x, I'm going to say a. Instead of saying y, I'm going to say b. Theta is good. What am I using? I'll accept an answer here. Instead of r, what is r previously was the radius? What does that correspond to in this new complex situation? Go ahead, Mari. Say again? You said the magnitude of the number? Yeah, magnitude of z. Yeah, that's what I heard. That's what I heard. I don't know what y'all are hearing. So yeah, instead of r, which is normally here, we're doing magnitude of z. So magnitude of z cosine theta, magnitude of z sine theta. All of that is super helpful to write down, as well as this other thing here. So I'm going to write a plus bi would equal magnitude of z cosine theta. So I'm going to substitute that. So magnitude of z cosine theta plus magnitude of z sine theta times I. And that's a whole lot of writing there, so I'm going to let you kind of think about that. A plus bi, that's our complex number. Z equals a plus bi. If I replace the a with z cosine theta, and I replace the b with z sine theta, then I get this. Now, mathematicians, we always like to take shortcuts and look at things that are all kind of the same. someone along the line, someone said, hey, look at this. This is, I've got a z here and I've got a z there in both of those terms. So what's something we normally do when we've got a z in multiple terms? Factor it out. So they said, hey, what do we write this? Z, and then put a parentheses, and what's left here is cosine theta, plus, and then what's left here is the sine theta, and the I. And then someone else came along and said, all right, well, let's, maybe the same person, I don't know. He said, I don't like the sine theta and then the I. It kind of gets confusing if maybe the I is in there or whatever. Let's write it like this. Let's say cosine theta plus I sine theta. Everyone's like, all right, all right. And then someone else, maybe the same person, said, well, let's be real honest here. Do we really need the bars and the parentheses and to say cosine and to say the sine, have all that stuff like there? What are the real pieces of information that we need? And someone said, well, we really need the z. And we need a way of communicating that it's cosine theta plus I sine theta. But we absolutely need that theta. So what's a way that we could condense all this? And they said, aha, the C, the I, and the S. So they said, let's write cis, and then write theta. So Z cis theta is has a special name. This is a complex number written in trigonometric form. Complex number, I'll just abbreviate it, trig form. And there's all kinds of stuff that you can do with that. Immediately, you can find the magnitude and the angle because they're literally right there. And it's two quick calculations to get you the x component and the y, or I should say the x component, the real part and the imaginary part, right? And I sometimes call this the sissy notation. So here's an example. 5 cis 20 degrees. Question. What's the magnitude? 5, 4, 3, 2. 5, that's right, okay. What's the angle? 20 degrees, okay, there we go. What is the real part? Now it's going to take a look. 5 cosine 20. Grab your calculator, throw that in degree mode real quick. The real part is going to be 5 cosine 20. Ladies, you take care of that. Gentlemen, you take care of the imaginary part. 5 sine 20. Ladies, just truncate it. Just give me one digit after the decimal. What do you got? Maybe 2 digits. Say it again. 4.7. Guys? 1.7? Seems likely enough. So that number, this complex number, in what we would call rectangular form would be 4.7 plus 1.7i. That's rectangular form of a complex number. We like trig form. We'll find out, maybe tomorrow, tomorrow's Thursday, some really neat stuff that you can do with that, okay? Let me give you another one just to see if we're on our toes. We might go exact answers on this, okay? So 3 cis pi over 6. All right, class. What's the magnitude? 3. What's the angle? Pi over 6. The real part, following that same pattern, it's going to be magnitude cosine the angle. So 3 cosine pi over 6. Now, whip out that trig chart there. So you have pi over 6 memorized. So remember, for doing cosine, that means find the x value. And what's the x value on pi over 6? 1/2.
So it's root of 3 over 2.
Root 3 over 2, okay. So 3 times root 3 over 2, so 3 root 3 over 2. The imaginary part, 3 sine pi over 6. So it's just magnitude sine angle. So looking at that same location, pi over 6, what's the y value? That's the 1/2. So 3/2. 3 cis pi over 6 turned into rectangular form would be 3 root 3 over 2 plus 3 over 2i. Real part, imaginary part, plus imaginary part. Okay. All right, very doable. I think we're ready for some problems. Mr. Greensword, I might need you to unlock those. And while he's doing that, you can definitely take care of, like, I think the first 2 problems, they're just graphic. Leave that, I'll erase this. I didn't know your pen. It's in the math shared folder. Sorry, just read it my drive. It's shared. Complex 2, yep. Ready to get it on? Let's do this, guys. Well, I know you guys this part. I think this is the same place. Show it. Hold on. Sure. All right, turn back to that front page. We'll make sure we're all on in the right answer. 5 minus I, so that's 5 on the real axis. 1, 2, 3, 4, 5, and then minus 1. That's going to go down on the imaginary axis. So there you go. And then negative 4, 7i, so negative 4 on the real, 1, 2, 3, 4. And then up 7, 1, 2, 3, 4, 5, 6, 7. Put it out there. Great. I'm looking forward to this homework. Turn the page. Sorry, this says negative 3 plus I. So, starting from the origin, what am I going to do first? Go left 3, and then up 1. That's good. Taylor, this one says 4 minus 5i. What am I going to do first?
Right 4 down 5.
Yep. Right 4, down 5, dot. Y'all probably already got this. Sorry for slowing us down. Let's look at the real problems, not these imaginary ones. Sorry, this is bad. Write each complex number in standard or rectangular form. Give exact values in your answers, not decimal approximations, so make sure you have that trig chart out so we can take care of that. I don't know about you, but radians just scare me. Not really, but that's what a lot of students say. So let's go ahead and start with the degrees first, right? Yeah, let's do that. So I like this one. 2 cosine 240 plus I sine 240. Or we could, if we really wanted to write that, I don't know why they didn't abbreviate, it would save them some electricity there. 2 cis 240. We don't have to do it, but Trey, what's the magnitude on this complex number? Keep going, and the angle? Yeah, okay. So now all we have to do is find the real part. And we've got a formula for that. It's the magnitude cosine the angle. Now, if you do cosine 240, so if you do 2 cosine 240 on your calculator, you might get lucky, and if it's like a 1/2 or something like that, then it'll be nice. But let's get in the habit of using our trig chart when they're asking for exact values of sines and cosines. So let's find 240 on the trig chart. She's got one she can share, or you can pull your one out there. So let's find 240. Now if we're doing cosine, what are we going to look at? The x value or the y value? X value. X value is? Negative 1/2. So the real is going to be 2 times negative 1/2. So 2 times negative 1/2 is just negative 1. Those of you who type on the calculator, you probably got a good answer on that. But the imaginary part, 2 sine 240, calculator is not going to be very friendly on that. So, Taylor, talk to me. You have a trig chart?
Yeah.
Sine of 240, so we're looking for the y value there. What do you get?
Negative root 2.
Okay, that looks like a negative root 2. So that 2 will cancel out with that 2, and we end up with negative square roots of 3. We found the real part, we found the imaginary part, now all we have to do is just sort of combine them. Bree, you want to give us a shot how to do that?
Negative y minus root 3y.
Anybody agree? Nod your head. Anybody disagree? Get a mean look from Bree. Looks good to me. We found the real part minus the imaginary part. Don't forget to put the I on there. And we're good. Let's do part A, which has 5 cis 7 pi over 4. So, not totally required, but good for us to practice. Ferrari, what is the magnitude of this complex number? And the angle? So, the real part we know is magnitude cosine. So that would be 5 cosine 7 pi over 4. And the imaginary part, 5 sine 7 pi over 4. So we're all looking at trig charts, and I'm looking at Sarah, cosine Positive, negative? Positive. Are you positive? All right. There we go. You said root 2 over 2? So, well, that's not too bad. It's just going to be 5 root 2 over 2. No way we can cancel 5s. 5 and the root 2, they're not going to do anything. Sorry, keep talking to me. What about sine of 7 pi over 4? Are you negative? Oh, positive. So negative 5 root 2 over 2. You're doing such a good job, sorry. Go ahead and finish this up. Can you turn that information into a complex number in rectangular form? Like this one? Just a little bit louder. Keep going. You are correct. Well, that's not too bad. And look at us. We're transitioning back and forth between magnitude, direction, and x and y components, and real parts, imaginary parts, just like we've been doing all year long. Give me thumbs up, thumbs down, class. We feeling all right on this? I think so. Number 4 looks like more of the same. Now, number 5. Robert, what's different about number 5?
It's in rectangular form, then you have to convert it to
That's right. It's in rectangular form, and we've got to convert it into trig form, sometimes called polar form. All right. Isn't it weird how all this stuff just sort of like laps and overlaps and anyway. So here they have the number z equals negative 5 root 3 plus 5I in trig form, sometimes called polar form. Express the angle theta in radians between 0 and 2 pi. So that means it looks like it would be kind of tricky. Now, one thing that we need to do is figure out which quadrant we're in. Okay? So that's always the hardest part, figuring out which quadrant we're in. All right, you have a guess which quadrant, 1, 2, 3, or 4, which quadrant we're going to be in? Say again. 2. Why do you say 2? All right, negative, positive, and the negative happens to be on the real part. The positive is in the imaginary. So looks like we're going to be right up there. So we've kicked over negative 5 root 3. We've kicked up 5. First, we're going to need the magnitude. And if you remember, we can find the magnitude through Pythagorean theorem. So we'll say the magnitude is the square root of the sum of the squares. So the square root of 5 squared plus negative 5 root 3 squared. So that's going to be 25 plus negative 5 times negative 5 is a positive 25. Root 3 times root 3 is 3. So we'd have 25 times 3, so that's 75 plus the 25. So that's 100. And the square root of 100 is 10. Okay, well that's pretty nice. So we've got magnitude of 10. Now when we talk about the angle of this complex number, in all reality, the angle theta is really this angle right here, the angle from the positive x-axis. So what I said here earlier probably wasn't completely accurate. That the angle theta is not always the inverse tangent of b over a. what I should have said is what we've been saying throughout this course here, is that theta ref is equal to the absolute value, or sorry, the inverse tangent of the absolute value of B over A. I can get theta ref right there, and then to figure out what actual theta is, I'm going to have to sort of use my head to figure out what that answer is. So we'll do theta ref is inverse tangent of the absolute value of 5 over, I can put negative 5 root 3, but that's going to, the negative will go away completely. We've got some different ways that we can do this. We can look at our trig chart, and that'd be nice. What I would recommend, though, it's kind of standard, is just go in degree mode. All right. So put a little star next to this, and let's go in degree mode. We'll use our calculator to figure out the degrees, and then it'll be a nice reference angle that we're all comfortable with, and we use the trig chart to just transition that over to radians. Okay. Now, when you key this in on the calculator, as always, you've got to be smart about this. I'm gonna walk around and make sure everybody gets it. You know, you're gonna do inverse tangent, open parentheses, 5 divided by, and here's what we need. We need both of these things in the denominator. So you're gonna have to put another open parentheses to say 5 root 3. Close the parentheses for the denominator. Close the parentheses for the square root. In fact, in the way that your calculator is set up, it's even more annoying than that, because when you do the square root, then it has an open parentheses, and so you can put 3. You gotta close the parentheses for the square root. Close the parentheses for the denominator. Close the parentheses for the inverse tangent. Although sometimes your calculator is really, forgiving, and if you don't have all those closed parentheses, you just hit enter, it figures it out for you, all right? Yeah, okay. But anyway, I'm gonna walk around. Grace, do you have an answer? 30 degrees? Yeah, when they're asking for something that's gonna be exact, that should be right. Let me walk around and make sure everybody is able to key that in. Yeah, make sure you degree mode. You have 5 parentheses 5 divided by. Hold on. There's one. There's a secret parentheses that you're missing on that table, and that's this one right here. It's going to be 5 divided by. So, yeah. Good. Yep. Pretty good. Oh, and then just do that. Using the brain right there. I like that. All right, got it. Any luck? All right. So, we found out that it's 30 degrees. All right, class. And so then using our head, using our mind here, what is theta? Which is going to hit over there and have a reference angle of 30 degrees. It's not, you said 60? Not 60. 60 would be from this part right here. But I'm going from the positive x-axis all the way over here. 150? How did you arrive at such a number there, Grace? Subtracting 30 from 180, yes, okay. So 180 minus the 30 gives us the 150. Now, en radiano, por favor. But, donde está el ego? Cuadrantu, dos. She says 5, 5, or 6. It's the verse right there, yeah. I mean, that's not, it's the one that's right next to it. All right, okay. Now, you like it? 5, 5, or 6? I agree as well. All right, so, gotta make sense of all this mess here. Write it in trig form. So, earlier we had 10 as the magnitude. Now we've found the angle, so we're going to write this like they had written the previous one. So we're going to say 10, open parentheses, cosine 5 pi over 6 plus I sine 5 pi over 6. If you want to write cis, you can. But Alex is going to force you to do that. But I think they actually have a sissy button. You just click the sissy button, and then you'll be able to fill in this, and this. And make sure we all know that like those two numbers are always the same. Right? I mean, it's always the same angle. We're never going to have cosine at a different angle from the sine. Okay? 6 looks like one that we can maybe give a try tomorrow. Let's look at 7 and 8, see if there's anything new wrong with that time. Find the complex number in trig form. Find the complex number in trig form. Okay, great. What we'll do tomorrow is I'm just going to make sure that everybody can solve at least one more, and then I'll let you work on the homework, okay? So class, just hold on to something, please. We got 1 minute left. So I need someone to tell me what we talked about today. Maybe like 3 of you.
Complex numbers in trig form.
Thank you for reading the title. All right, so now you're out. Somebody else though, what's something that we talked about today?
Converting rectangular to trig form.
Okay, converting rectangular to trig form of what?
Complex numbers.
Of complex numbers. How to graph what? How to graph complex numbers. Very good. All right. Well done. Learn about the sissy form. And when the clock strikes 12, you can all go to sleep. Ding, 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 there's a bell.
Huh? No. Huh?
You got more.
Ariana wishes.